All right, good morning, good afternoon, good evening, depending on when you're watching this video. We're in week 2 of your statistics course. On Tuesday, we just covered, we started in chapter 4, covering linear regression. This series of videos that you'll watch will cover the rest of the sections that are in chapter 4. So our goals today are to cover regression analysis, more or less modeling linear trends and evaluating a linear model. Okay, so let's get to it. So here we'll talk about modeling linear trends. And so from the previous lectures, we were saying we're in this observational study. We are not establishing a cause-effect relationship. Each measurement has 2 observations, and pretty much given one variable, we're trying to predict the other. Okay, so we've seen the scatter plot, and we've seen the correlation coefficient, and so now we're ready to build our model so that given value of x, we can predict y. So the goal for this lecture, for this particular section here, is we want to create the regression line. So pretty much what we want to find is this red line here. Okay, this red line. So this is the data set that we've seen before, where we're looking at weight and running speed. And we looked at the scatter plot. We said, yeah, you know, as the weight increases, the running speed will decrease. And we calculated the correlation coefficient for this data set, which is like negative 0.77. And so now what we want to do is, given a weight, can we predict the running speed? And so pretty much what we get here, what this red line gives us here, is the typical or the average running speed for a given weight. Right? So this red line is really just a bunch of averages, bunch of average running speeds for over different weights. So as far as the equation of this line, well, this is just a straight line, right? So we've seen these types of lines in algebra. And so that's where we start off here. We say, well, the regression line is a tool for making predictions about future observed values. Okay, so we call from algebra that equations for straight lines contain a y-intercept and a slope. The equation for a straight line is usually given by this formula here. Okay, y is equal to mx plus b, where y is our dependent variable, m is our slope, x is our independent variable, and b is the y-coordinate of the y-intercept. So, and really m, the letter m just tells us how steep the line is, and the letter b is the value of y when x is equal to 0. That's just definition of the y-intercept. But for statisticians, we write this whole thing backwards, and really every letter, every quantity has context. So as we learn in chapter 1, 2, and 3, all the numbers that we deal with are context. So none of our numbers stand alone. Our numbers represent something, whether it's an average speed or average height, they all represent something. So for statisticians, we write the regression line as so. We say y is equal to a plus bx. So a is where we put the y-intercept first, and then b becomes our slope. Okay. And so the reason we do that is because later on, well, we won't see it in this class, but we can add more terms here, like x squared and x cubed, but we won't do that here. Okay, so it says where every quantity is within context, right? That is, they place numeric summaries on the association. Okay, and we use the variable x to help predict the typical value of variable y. Okay, so let's look at an example here. Okay, so here we're gonna visualize a regression line. Okay, so here, if we go back one slide, you see how this line was drawn here. It's kind of, it's the best representation of the pattern that we're seeing here. Right. So what we're going to get to is, well, how do they find this line, right? What is the y-intercept and the slope of this line? How did they pick this line? So for now, we're just going to kind of eyeball it. So in this data set here, we predict the daughter's height given the height of the mother. So below we have a scatter plot. Okay, so here the x-axis is the height of the mother, and the y-axis is the height of the daughter. Okay, both are in units of inches. And remember, what goes here in the x-axis, that's the explanatory or predictor variable. Okay, but the x-axis goes the explanatory variable. And the reason we call it that is because we're using this variable to help us predict that variable, right? So we're trying to, given the height of a mother, right, can we predict the height of the daughter, right? So we're trying to use height of mother, right, to explain or predict the height of daughter. Okay, so this is of course our response or outcome variable here. Okay, so the thing is, if you look at this plot here, is here we have a scatter plot of all of all of these. For each mother-daughter pair, we record their heights. Okay, and of course, and we say, do we see a linear association here? Okay, so take a look at this. Do you see a linear association? It kind of seems as mother's heights gets larger. Seems like daughter's heights gets larger. So here we see a positive linear association. Okay, so here our correlation coefficient, if we're to calculate it here, would be equal to 0.49. Okay, indicating moderate strength for positive linear association. So the shape of it is linear, right? It's definitely positive because his mother height is increasing, daughter's height is increasing, right? And it's obviously a linear association. There's a lot of scatter here, so that's why we're getting a value that's not so close to 1, but 0.49, hey, it will work with that. Okay, so that's why I say moderate strength for positive linear association. In different contexts, I mean, of course, R close to 1 is always going to be strong, or R close to -1 is always going to be very strong. But in some contexts, especially like in biology, sometimes a 0.49 is a very large correlation coefficient. But just because there's a lot of noise in the data. But I mean, not to make it confusing or anything like that. But here we'll just say moderate strength. But we do see a clear pattern here. Okay. So now let's think about the best linear model. So when we talk about the linear model or the regression line, we're talking about these red lines here. Right? So here I have one model, I have my second model, I have my third model. So all of these models, I mean, they're at least lining up to what we see, right? A positive linear association, right? Linear, it's a straight line. Positive, obviously the slope of these lines are all positive. Right, but which of these is the best? Okay, so just take a look at it and really what this line means in context, right? So they all mean something in context. We're saying the predicted height of daughter is equal to some constant plus the product of some constant times the height of the mom. Okay, so give me the height of mom and I can give you the predicted height of daughter, or daughter, I guess I should put a T there, huh? Okay, daughter. Okay, so A is the y-intercept and B is the slope. So pretty much what we're trying to do here is we're trying to guess what A and B are. Okay, so I mean, look at these here. Which one do you think would be the best? Okay, so now the cameras are on your computer now. They're recording. So I'd like you to raise your hand if you think this is the best line. Okay, I'm showing 3 of you think this one is. Okay, now I'd like you to raise your hand if you think it's this curve here. Okay, got about 15 responses so far agreeing with this one. Anyone else? Raise your hand. Got about 25 responses here saying you guys believe that it's this curve here. And last but not least, raise your hand if you think it's this one here. Okay, cameras are on your computer. I'm recording these numbers here. I see about one of you. Okay, just one. Okay, so good thing the majority got it right. This is the best fit here. As you can see, this line's pretty good, but you see it's a little under. Right, it's underestimated a little bit because it's kind of shifted down. This one kind of cuts the data points in half, kind of perfectly, right? Goes right through the middle. And this one's a little too high, right? It's a little high. Okay, so good job, everyone. And by the way, I cannot see the camera. I was just kidding. But I wonder, did you raise your hand? I want to know, did you raise your hand? Okay, because yeah, I can't see. Okay, this is just a video. Okay, all right. So which regression line? So actually, in Desmos, it will find us this curve here. This curve here. So it says y is equal to 29.917 plus 0.54 times x. So remember, x is the explanatory. That's the height of mother in inches, and y. So that's the equation of this line. But remember, this here is maybe what you see in algebra, but it's useless to us, okay? Because we always have to interpret it within the context, okay? Just like the mean, standard deviation. I mean, calculating them is not enough. We need to know what they mean within the context, okay? So really, what this means here, it means the predicted height of daughter is equal to 29.92 inches plus 0.54 times the height of mom. Okay, so pretty much what I can do now is plug in the height of mom, and I will give you the predicted height of daughter. And really what we're saying is the average height of daughter. Okay, that's really what it is, right? Because if you look at this red line here, if I did 65, okay, let's say the mother's 65 inches. Well, what's the predicted height of the daughter? Well, let's go here. Boom. Sauce. Roughly about 64 inches, right? So the daughter here is still pretty tall, right? Taller, a little bit taller than the average, but not taller than the mom. Same thing here. If we did about 68 inches, boom. Sauce. Okay, so here the mother we're saying is about 68 inches. So the expected height of the daughter is around, 66, 67 inches. So the daughter is also, pretty tall, but not taller than the mother. Okay, so I'm picking mothers that are like taller, right, in the taller range, right? So what this is telling us is that their daughters are also going to be tall, but not as tall as them. Okay, and if you pick here, like in the shorter end here, right? So here, let's pick around 56 inches here, or 57 inches, right? So let's find, given mother, let's find the predicted height of daughter. So I go here, what's the height? Boom. Okay, so I get about 61. So here we're saying that given the height of the mom is around 57 inches, the height of the daughter is going to be about 61. So they're still going to be on the shorter end, the daughters, but they're going to be a little taller than the mom. Okay, if I picked one here, maybe I picked one right here, 58 or something like 58 inches. Okay, boom. Sucks. Okay, so we're saying here about 62 inches. So say, hey, if your mom is on the shorter edge, I guess at 58 inches, the daughter is also going to be on the shorter range, but she's going to be a little taller, right, than the mom. Okay, so this is what we call kind of a regression towards the mean, or the regression towards just being average. Okay, so it's saying, if you're really, really tall out here, well, eventually that's going to stop. Okay, and then your kids are going to start being short. They're going to be maybe just as tall, but a little shorter. And then your family's just going to, generation by generation, their heights are going to regress towards the mean, right? And then same thing here. If you're really short, well, guess what? It's not going to last forever for your generation, right? Because your kids are going to be a little taller. Their kids may be a little taller, and they're going to regress towards the mean here. Okay, we'll talk more about that. So how do we use this line? So now we can use this red line to predict. Okay, so pretty much what we want to do here is, let's plug in, let's use this line here to predict. So what we want to do is we want to predict the typical height of daughter given the height of mother is 66 inches. Okay, so what I plug in here is I plug in my 66 inches for height of mom here. I do 0.54 times 66 plus 29.2, and I get 65.56 inches, right? So this mom is a little taller than on average, okay, taller than the average height, okay? And if you look at the height, the predicted height of her daughter, well, she's also going to be taller than the average, but not taller than the mom. Okay, and this is just an average, okay? So really the height of this regression line, okay, this red line that you see here, the red height, you know, when I was going boom, sauce, the sauce part that I was doing, that's the height of the line for this here. So it says the height of the regression line provides the typical mean height of daughter for a given height for mother. Okay, so this number that we're getting here, it's an average. Okay, so it's saying, you know, well, the heights, if we have several moms with the same height of 66 inches, well, their heights of daughter is going to vary. Okay, it's going to vary. Okay, some may be a little high, some may be a little lower than 65.56, but they'll be centered around this value. Okay, and on average, the height of the daughter is going to be 65.56 inches. Okay, so if I were to go here's 66, right? So this is where the red, this red dot right here, right? If I go sauce, right there is about 65.56. So that's average, right? But if you look at the space here, right, there's some heights that are above the mean, some heights that are below the mean, right? But if you just draw this vertical line here, right, you kind of see that this red line is more or less right dead center. Okay, this is like the average, like the center. Okay, so that's why it's a typical or a mean. We can think of these predicted heights as a mean. Okay. So what we're talking about here is this phenomenon in which we call a regression towards the mean or mediocrity. Okay, so we're saying mothers that are taller than average tend to have daughters that are also taller than average, but closer to the overall average height. Right, so remember in the previous example, the mom was 66 inches, which was taller than average, and the daughter was 65.56 inches, right, on average. And so we're saying, well, that's still taller than the average, but not taller than the mom. Okay, and then we say mothers that are shorter than average tend to have daughters that are also shorter than average. Okay, but also closer to the overall average height. Okay, so in this case, we're saying that, remember on the lower end, right, where the mother was maybe 55 inches tall, well, the expected height of their daughters, they're also going to be relatively short compared to the average, but they're going to be on average taller than the mom. Okay, so they're kind of all going towards the average height, right? So this is what we call regression towards the mean, or regression towards this here. So I mean, really what we're talking about is an average line. That's really what it is, right? This line represents a bunch of different averages of the daughter's height over a bunch for different values of mother's height, right? But Sir Francis Galton, who kind of discovered this phenomenon of regression toward the mean, right? We're saying that, okay, these heights, if you're really tall, well, guess what? Over time, your heights, they're going to regress towards the average height. And if you're if you're on the shorter end, then guess what? Over time, in generations, that height's gonna, the mean height for your family is gonna move towards the average height. Okay, so he discovered this regression towards the mean. Okay, meaning that, you know, no matter how special you are over the generations, you're gonna return to just being average. Well, maybe not you, but you know, generations down the line. Okay, but where we see this more recently, is in the Sports Illustrated Jinx. So I'm not sure if you have heard of this before, but there's a phenomenon out there called the Sports Illustrated Jinx. And so what was happening is that these athletes were being recognized for their outstanding performance in their sport, that Sports Illustrated invited them to be on the cover. And what happened to a series of players is that after they were on the cover of Sports Illustrated, they had a horrible season in comparison to how it was before. And so this kept happening, this pattern kept happening where these athletes, one of them, if you're at all familiar with football, is Tim Tebow. And if you're not, don't worry. But he was a star college athlete, and he was on the cover of Sports Illustrated, and now I don't think he plays any sports anymore. Okay, but what happened is that so these star players, it's like season to season, we rate how good they are, and so these athletes were like just had the best season, right? And Sports Illustrated wanted them on their cover, and that was an indication that they had an awesome season if they made the cover. So pretty much they were at the very far end of the spectrum as far as good seasons go. So if they made the Sports Illustrated, I mean, they had nowhere to go. They couldn't do any better than that season. So the next season had to be worse. And so that's what they're recording there is the regression towards the mean kind of phenomenon there. And so what happened is that Sports Illustrated, they couldn't get anyone to agree to be on their cover. And so they just decided to put this black cat there, right? And talk about the Sports Illustrated jinx. Is it real? And so this thing, you can look it up, Sports Illustrated jinx, and they're recording it over time. And it doesn't happen all the time, but it happened often enough to scare some people away from wanting to be on this cover. Alright, so before we move on to further explain this regression model, let me just show you in StatCrunch how we create this, how we have StatCrunch find the coefficients of this line. But really quick, as far as how, I'll give you the gist as far as how we select the y-intercept and slope. It's kind of beyond the scope of this class. The good news is that StatCrunch does it for us, okay? And we could do some things by hand. I have some formulas for you coming up soon. But what it does here is that, because when you were eyeballing, when I gave you the 3 possible regression lines, you kind of picked the one that cut through the center. And really what you were comparing was the regression line with the actual observations. And really we were moving the line and keeping track of the space between the actual observations and the line. So this is sometimes referred to the error, this distance here. So this is at the actual, this height here gives us the actual height of the daughter, while this here gives us the average daughter height. And so pretty much this distance here is how much our line is off by. So pretty much how the y-intercept and slope, how they're estimated, is what we do is we add up all these errors, we square all the errors, and then we add them up, and then we try to minimize that quantity. And so how we do that is through calculus. It's an optimization problem where we optimize with respect to A and B, right? So, but what it does is it gives us a line such that if you pick any other line, and if you add up the errors for that line, it will be more than ours. Okay, it will be the same, or well, it will be more than ours. Okay, so pretty much that's how this A and B are selected. We pick this, these estimates are selected such that these errors are minimized. Okay, so that's as much as I'll get into it. Okay, but you'll just have to believe me for now. In order to really kind of jump in there, we need calculus to really prove those results. Okay, but let me show you in StatCrunch really quickly how we calculate some of these results. So here, what we're doing here is so here is my data set for mother and daughter heights. Okay, so here I could do a graph, and I could do scatter, and I can do, let's see, well, we want explanatory to be mother, and we want the y, the response variable, to be daughter, and then we can compute, and then that's my scatter plot. Now, how did they get the equation of the line? Well, now we can go to stat, okay, and then we go down to regression, and then we do simple linear. Okay, now these other ones are very cool. Okay, they're very cool, but I'm not sure if I have time to talk about these in stats, but oh wow. Okay, but for now we'll do simple linear. Okay, we'll do simple linear. So x variable, remember that's your explanatory variable, so that has to be height of mother, because we're trying to use height of mother to predict height of daughter. Okay, y is the response or the outcome variable, so that's daughter. Okay, and here, what I want to do here is go ahead and compute. Okay, so what we get here is a table with some output. Okay, so here we get, this tells you dependent variable, the explanatory variable is daughter, independent, response variable, outcome variable is daughter, independent explanatory variable is mother. Here's the equation of the line. Okay, here's our sample size, correlation coefficient, and this is other stuff that we may talk about later, but this is just kind of doing a test. What these are doing are kind of a test to see whether your model does any good. Okay, so so this is the output here. The main ports we can use this right here. Okay, but you see StatCrunch gives us a very nice layout, and if you click here, it'll actually show you the scatter plot with the fitted line over it. See, if you hover over, it'll give you the equation of the line. Okay, and if this line is too thin, you know, I always think it's a little too thin, you can always edit here, and let's see here. Okay, well, I'm not gonna mess with that right now, but anyways. Okay, but anyways, so you see it gives you the nice nice scatter plot with the fitted line. Okay, so very nice option here. So options too, you know, you can edit, you can always kind of make this a little nicer. So like as far as labeling, like really it should say, you know, we could do mother, and we could put, you know, we always put the units there, inches, right? And then here we could put you know, daughter, and we could put in inches, right? And so if you compute it that way, what we get here is we get the same output. Nothing changed with this output here, but in the graph you see it's properly labeled mother, and then you have the units inches, daughter, and we have the proper units here, inches. So just some nice things you could do with StatCrunch in calculating these lines here. Okay, all right, but I think I'll leave it off there for now, and we'll take a break and have you answer some questions, and we'll come back and continue our talk on the regression line.